So after the math part, therefore, the first thing we want to talk about is the most, let me say, fundamental aspect of mechanics, which is deformation, and that will be covered under strain and compatibility. Just like for the math part, some part of it will be a review, and some part of it will be eventually new for you. Okay, so let's first begin by talking about displacement. Although we understand what it is, it's something that we rarely explicitly refer to in undergraduate mechanics. So let me draw some cartoon here. So this is some object, okay? So believe it or not, it's just a domain that indicates an object. So it could be a desk, it could be a car, airplane, it could be a human body. We don't really care what it is. So I'm going to call this the original or the undeformed, referring to the fact that presently I'm not applying any forces, I'm not accelerating the subject. It's the original state, or sometimes we'd like to refer to that as the configuration of a structural domain. So that structural domain could be anything that you're trying to analyze. Okay? And let me call that structural domain, right? It's a three-dimensional domain. Let me call it R. Let's make it calligraphic R. Okay. So I will choose a coordinate system here. I will have an origin, right? Let's say a Cartesian basis. And with respect to that basis, I will have eventually a position vector that shows the position of a point within this domain, within the structure. Now, what will happen is that eventually this object will be subjected to forces, and because it is subjected to forces, it will start moving. And not only does it move, but it will also get deformed. For instance, it will get squished because I'm applying from, let's say, pressure from all sides, right? So it will move, it will squish, or it will stretch, it will change its shape, it will be torsioned, etc. The point is eventually this thing will move to a different location, and it will probably also look different, okay? So let me indicate this new configuration of the body with R prime. So this will be the deformed configuration. And now at this point, I'd like to immediately write that this is an exaggerated picture. Exaggerated picture in the sense that in this course, we will solely talk about small deformations, okay? So in other words, small deformations meaning that, or small displacements, this object, it can move, it can deform and change its shape, but they will be slight. You will usually be barely able to see it with your eyes. So in reality, if this is the original configuration, the deformed configuration will change just a tiny bit from the original one. So this is R prime if I have really small deformation. So this one, therefore, is the R prime that I would have for large deformation. We are interested in this course in small deformation. I'm nevertheless drawing this picture to make some quantities a little bit more clear, right? So what does, again, small deformation mean? I have this board. Right now, I'm leaning on it. I'm applying a significant amount of force on this board. This board is certainly deforming and changing its shape, but you really cannot see much, right? So this is a perfect problem for linear elasticity. Okay, so that's the original position of a point. Of course, afterwards, it moves to a new point, and that new point, let's indicate with y. So this point has moved by a certain amount to a new location, y, and the quantity that relates these 2 points will be u, which we will call the displacement vector. Okay, so this point is displaced by an amount u from x to y. So we have u, it's a displacement vector, and the displacement vector will be different in general for different points in the structure, and it might depend on time because this thing perhaps is accelerating. Okay, so its displacement vector will increase with time. So that's dependence on both position and time. So that's our displacement vector. Sometimes I will call it the displacement field. So a field is a function sort of that is distributed over a domain. So for instance, I could talk about the temperature field in this room. The temperature has a distinct value at every point within the room, so it's like a field. So sometimes this is a preferred terminology, displacement field or displacement vector. What is important is that this thing has to be small in magnitude. We're talking about small deformations. So the original position of a point is x, and it is eventually displaced by an amount u, and that gives you the current value of the position, which therefore is a function of position and time as well. You can write this in components. I have yi equals xi plus ui, and ui depends on all components of the position as well as time. You can go ahead, calculate, for instance, velocity and acceleration. So velocity would be del y over del t, right? I take a derivative, partial derivative with respect to time, but this thing does not depend on time. It is the original location of the position. Original location, it's defined by definition independent of time. So a derivative with respect to time, it's 0, so it's simply del u over del t. And similarly, I can define acceleration, which is del square y del t squared. So that would be del square u over del t squared. Okay, so now I'd like to introduce one quantity that will be important for us. And that is the displacement gradient. Now, the displacement gradient, it is defined as, well, as the name suggests, it's the gradient of the displacement vector. I will call it h. Okay? And therefore, using the definition of the gradient, h ij is equal to del ui over del xj. Okay. So I can put that in matrix form as well. So h is u1, 1, u1, 2, u1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. So now the displacement gradient eventually is not going to be really used by itself, but we're going to use it to define even a more important object, which will be the strain. Okay? So let me make a note here because it's going to take a while before we come back to an explicit expression for strain in terms of h. First, what I'd like to do is, because it's been a while perhaps that you've made use of strain and stress in detail in your courses after the fundamental mechanics courses, I want to go back and remind you the basic strain concepts. Okay? And I'd like to do that first with normal strain and then with shear strain. So let's recall definitions of strain. Okay? So this is essentially ME 231, but I'm going to do it very, very compactly. So the way we defined the normal strain in ME 231 was as follows. I took, again, a structural domain. On the structural domain, I picked 2 points A and B, not necessarily close to each other. And these points are at a distance, let's say, L from each other. And this is a certain direction. That direction, let's call N. Okay? And just indicates the direction that links A to B. And now this object deforms. And again, I'm exaggerating, but this is a small deformation. So in reality, the difference between the deformed and the original one would be very slight. But let's exaggerate. So let's say this is the new picture for the deformed object. And now, point B moves to a new point B prime. A moves to a new point A prime. And suppose this was a line that I had drawn on the object. And so because the object is deforming, this line will deform as well. So let's say that line looks like that. Okay. So A prime and B prime, they are still somehow, if you like, linked by a dotted line. But the length of the actual line I had drawn is now different. It's L prime. And so what we had done in ME 231 was we defined an average. So that's the first keyword. We start with an average value. And we're looking at normal strain. And we're not looking at any strain. We're looking at the strain along this particular direction, N. And the way it was defined was, so first of all, the normal strain. I'm looking in the direction N. And I'm looking at an average value. And that was defined as the change in the length of the line I had drawn. So that's L prime over L divided by the original length. And that's, of course, a dimensionless quantity. Now, however, we talked about this in 231. And we said that, well, strain eventually is something that is defined at a point. So strain at a point can now be defined, starting with this average concept. And at a point, what I need to do is to talk about a point. Let's say I'd like to talk about point A. This thing is too large. I need to make this line smaller and smaller. In other words, B needs to approach, or needs to be as close as possible, or infinitesimally close to A as possible. And B is approaching A along this same direction, and it's not changing direction. So limit as B goes to A along N. And I take the same object, so in other words, the average strain. And that gives me the pointwise strain at N. So epsilon N is now the normal strain at A along direction N. That is as much as we had done in ME 231. So now I'm immediately going to generalize, take one step ahead of 231, and I'm going to try to put strain, normal strain first, on a more mathematical basis. Okay? So for that, let's consider a slightly more general deformation. So let's say we consider now multiple components. So not only along some particular direction N, but in a general setting, in a Cartesian, let's say, coordinate system. I'd like to consider multiple components, and I'd like to do that in a 2D Cartesian setting because that's the simplest. So again, I will take an object, and that is my 2D plane, x1 and x2. And let's say I have my point A here. That's point A. And A has coordinates x1 and x2. But I want to also refer to the point explicitly, so I will, in this case, put a superscript A. Similarly, I will have a point over here, B, and this point will have coordinates x1b and x2b. Okay, so then I will first of all connect these 2 points. So This could be the direction I'm looking at. I'm not going to do that. That would deliver me a result more closely related to that. I want to look at the individual directions, the x1 direction and the x2 direction. So here I have a distance in the x1 component. Let's call it delta x1. Here I have a distance in the x2 component. Let's call it delta x2. And eventually what's going to happen is, because this object is deforming, each point will move by a certain amount. It will be displaced. Okay? So let's say that UB gets displaced by U1B and U2B, while A gets displaced by U1A and U2A. Okay? So both of these points, due to deformation, they will move. All right, so that's pretty much the setup. So now we just need to analyze it, right? Making use of those concepts. The first thing I'd like to do is pick a direction. So let's, for instance, concentrate on the x1 direction. And let's observe, for instance, I have point A. Point A moves from x1A to its new position. That new position was indicated with y. So it's y1a, which is x1a plus u1a. And similarly, for instance, mu moves from x1b to y1b, which is x1b plus u1b. So now I can go and have a look at the original distance in the x1 direction between point A and B, and the distance between A and B after both points move somewhere. So the original distance, delta x1, the distance between the 2 points along the x1 direction before deformation, is simply x1b minus x1a. And the distance after deformation is delta y1, let's say. And that's equal to y1b minus y1a. So if I plug in these expressions, I have x1a plus, x1b plus u1b minus x1a minus u1a. And so I have delta y1 is that minus that is delta x1 plus u1b minus u1a. Okay, and let us call this delta u1. So that's the difference in the displacements along the one direction of the 2 points that I am particularly looking at. Okay, so I'm going to go ahead and do what I did on this board. First, I'll define an average strain, and then I'll define a pointwise strain. So first, let's do the normal strain. So normal strain along, in this case, I'm looking at the x1 direction, so I'm going to be looking at the normal strain along the x1 direction. And first, I will talk about the average value. So now, my notation is as follows now. It's a little bit different from 231. Normal strain, still epsilon, but I'm looking at the one direction, but I'm repeating that index twice for a purpose. So epsilon 1, 1 average. So epsilon 1, 1 average is equal to simply the change in the length. So the original length is this one. Sorry, the final length is that one. The original length is this one. And so it's delta y1 minus delta x1 divided by delta x1. And so that is equal to simply delta u1, right, the top part, over delta x1. Okay. So that is the average normal strain along the x1 direction. And now I can also define the pointwise value by taking the limit as b approaches a. Now, as b approaches a, essentially, so of that quantity, del u1 over del x1, what is happening is, mathematically, this delta x1 is going to 0. Distance is shrinking. And I'm looking at the same ratio, delta u1 over del x1. And the result of this operation is nothing but the partial derivative. Right? This is the definition of the derivative. So del u1 over del x1. So it turns out the pointwise strain at point A, right, and that's a normal strain, and I'm looking at the x1 direction, is associated with the derivative of u1 with respect to x1. So eventually notice that I'm using a partial derivative notation and not an absolute derivative because u1, it's a function of position. It depends not only on x1, but on x2, x3, and it also depends on time. So the derivative I'm taking it's with respect to x1. It's a partial derivative only. Okay, so. All right, so normal strain at point A along the x1 direction. We could have repeated this exercise similarly for the x2 and x3 directions. And if we do that, based on this approach, we would obtain the strains, the normal strains along the x2 direction and the x3 direction. For normal strains, along the 2 direction, you would be looking at the U2 components, and you would eventually, it turns out, just repeat the exercise yourself, you would be obtaining a derivative with respect to 2, and epsilon 3 would be U3, 3. Okay. So that is now a mathematical expression, a result that relates the displacement field or the displacement vector as a function of position explicitly to the strain components. Okay. And notice that, so that is now epsilon 1, 1. So these are all diagonal components, right? 1, 1 component, 2, 2 component, 3, 3 components. OK, so this part you knew. So in a sense, this part is new, right? Questions so far, right? If you notice, I followed exactly the same procedure as I did for this 231 level approach, right? It's just maybe a tiny bit more messy, but in the end, it's the same approach. OK, so we've done the normal strains. OK, so let's go to the shear strains. And also recall and link shear strains also with the displacement field. That's also something we had not done in ME 231. Let's do that as well. And I'll begin again by recalling what we had done in ME 231. So this is a original configuration of a structure. I will pick 3 points. I'm going to pick these 3 points in a particular way such that these lines are perpendicular. This just makes my life more convenient. And this direction, A to B, as before, I will call it the direction N, and this is a perpendicular direction. Let us call it T. So this angle, by my choice, it is pi over 2. It did not have to be pi over 2. It could be any other angle, theta, but I chose it to be pi over 2. OK. So now this object will deform. I will have a deformation. And that deformation, again, I like it to be small, but I'm exaggerating. So after deformation, the object loses its shape, and all of these points will move to new points, A prime, and let's say B prime, and eventually C prime. So that is a new direction N prime. That's a new direction T prime. And the lines also, they have deformed. These lines which I had on the original shape linking A to B. So let's say this one looks now like this, and the line connecting A to C has also deformed, and it looks like that. So what we will do is we will define an angle that links these new directions, N prime and T prime, and let's call it the angle, a new angle, theta prime. And using those angles, the new angle and the old angle, I can define now a shear strain. Now, with this picture, that shear strain is going to be an average strain. I'm talking about the average shear strain. And I'm not talking about average shear strain with respect to any choice of N and T. They could have rotated in any particular way. I'm choosing this particular pair. So strain with respect to and T directions. Okay, so the notation we had used was gamma for shear strain in 231, and the directions I have chosen, they are N and T, and I'm looking at the average value of the strain. And the definition was the change in the angle, but a slightly strange choice. It is the old angle minus the new angle. Okay? So that's the old one, and that's the new angle. So if, therefore, this is greater than 0, that means new angle is smaller than the old angle. Angle decreases. And if it is less than 0, it means that the angle increases. Okay? That's the particular choice that one makes. And also, we recall that when I write gamma and T, so the purpose of and T is just to indicate this particular pair of the directions. The order in which I write them has absolutely no effect on the result. So I might have as well written, instead of gamma and T, gamma Tn. The order of the indices do not matter. OK, so now that's the average value. But I'd like to define, again, the strain at a point, in this case at point A. And we will again do it through a limit procedure. And the procedure is that I want to be infinitesimally close to A. So B needs to approach A along that direction. C needs to approach A along that direction. So limit as B goes to A along N, and C goes to A along T, the limit of the average shear strain. So theta minus theta prime. And that gives me the pointwise shear strain with respect to NT, gamma NT. And that is equal to gamma Tn. It's the same thing. OK, so that's the shear strain at A with respect to NT. We've got the 231 stuff out of the way. That's what we had used in 231. The major thing here is that shear strain has to do with change in the angle between the axes as the material deforms. The axes change the angle between them. Okay? So now we'd like to build upon that and link shear strain to displacement field as we have done for the normal strain. And to make that a little bit, let's say, not too mathematical, I want to build 3 examples that will sort of indicate what that relation should be. So again, I will consider multiple components. So there will, in general, be U1 and U2, etc. And I will have multiple axes, x1 and x2. And I'll do that in a 2D setting. And I'll use Cartesian coordinates. So let me draw, first of all, here, try to squeeze in 3 pictures. The first one, so in fact, all of them. they will have some simple representation of deformation in the x1, x2. And in every case, I will start with a original configuration, coordinates 1, 1, it's a square. There might be a third dimension. We don't care about that. It's a hypothetical 2D scenario. So that's the original configuration of the structure. It's a square. Okay. It's the second one, and that's the third one. Okay. So now I will, this is the original square. I will deform each one in a slightly different way. The first one I will shear along the x1 direction. So after shear, this is how the block looks. Okay. The second one I will shear in the x2 direction. And after shear, this is how it looks. And the last one is a little bit more tricky. I'm going to shear it both in the x1 and in the x2 direction. So it's a superposition of this onto that, or vice versa. So if you combine them, what's going to happen is that it's going to look like a trapezoid, but a rotated one. It's going to look like this. Okay. So blue is deformed, dotted black is undeformed. Okay, so the displacements. The displacements are always small, right? I mean, even this is exaggerated. But let's say the displacement along the x1 direction is a. Just remember, it is much, much less than 1. 1 is our representative dimension here. Okay, and likewise here, I have a displacement, let's call it b. Again, b is much, much less than 1. And here, the displacements are, again, a and b. All right? Again, much, much less than 1. So now, the old angle, I will look at the x1, x2 plane, and I will try to analyze the shear strain. The old angle is in every case pi over 2, as I have picked in my original picture. And the new angle, so this would be the new angle. Let's, in fact, indicate here. So that would be theta prime. That would be theta prime. And that would be theta prime. Now, the difference between the old angle minus the new angle would be the shear strain by our definition. So this angle here, it's equal to gamma 1, 2. Right? I'm not putting average, assuming these deformations are very, very small. This is going to be exactly, in fact, the pointwise shear strain, gamma 1, 2. And here, this is equal to gamma 1, 2. I could have written, notice always, gamma 2, 1. It doesn't matter whether I write 1 or 2, 1, 2, or 2, 1. And here, the old angle minus the new angle is a sum of these two angles. So gamma 1, 2 is the sum of this angle with that angle, right? Okay, so we are in good shape. So now we just need to analyze this deformation. So why don't you lay your pencils down for a second, and let's have a look here. And I start with this picture. So again, my aim is to somehow relate shear strain to the displacements that I have here. So the first thing I will do is I will try to characterize this in terms of the deformation. So of course, tangent gamma 1, 2 is a over 1. But gamma 1, 2 is so small because a is so small that this is approximately equal to gamma 1, 2. And that's equal to a. Okay? And likewise here, the tangent of gamma 1, 2 is roughly equal to gamma 1, 2. And that's equal to b. And in this case, gamma 1, 2, because now I have two tangents, essentially, it's going to be a plus b. Okay? So these are the shear strains. I know what they are. What I just want to do now is relate them to displacement. Now, to relate them to displacement, I need to write the displacement field for this block. Originally, it's a square, and now it becomes a trapezoid. Now, the motion of every point you see, it's only in the x1 direction. Nothing moves in the vertical direction. So U2, by construction, is at all times equal to 0. That's the easy part. And likewise here, if I look, there is a motion clearly in the x2 direction, but nothing moves in the x1 direction. So in this case, the easy part is U1 is equal to 0. Now, in this case, neither U1 and U2 are 0. But let's go back. So U1 here, what is that equal to? Let me first write down the result and tell you about it. Okay, so U1. First of all, this point is not moving anywhere. So if I'm at x2 equals 0, U1 should be 0. Okay? If I move to x2 equals 1, U1 is A, right? And here I see a line which suggests that, so it's not like a parabola, it's not some strange line, it's just a straight line, which indicates that the relation that takes U1 from 0 to A, as x2 goes from 0 to 1, it's a linear relation. So it's AX2. That's the argument I make. And that relation is the same whether I'm looking at that point or that point. Here I see a similar picture just translated. Okay? So in fact, the displacement field for this picture is given as AX2. Now you can go ahead and do the same sort of argument for this case, and you will find that in this case, the displacement field is Bx1. For instance, if I look at that point, it moves up by B. It's at x1 equals 1. Here, it doesn't move anywhere. Here, I see a line, straight line that connects those 2 points. So the relation must be linear, and that's it. And the last problem is a superposition of these two. Okay? So in other words, here, U1 is equal to AX2, and U2 is equal to BX1. And so if you impose this displacement field on this dotted square, you will get this blue trapezoid. All right. So now let's start. And I know that this is the result for the shear strain. Now I try to relate it to the displacement field. And I just try to do a simple observation. And my observation is that I noticed that A, which is gamma 1, 2, is del U1 over del X2. Right? It's del U1, del X2 gives me A. So I suspect, is this equal to perhaps gamma 1, 2? The answer is no at this stage. Okay? So now I go to this picture, right? And I notice that gamma 1, 2 is equal to B, and I notice that it is equal to del U2 over del X1. So I could also ask myself, this relationship is so suggestive that perhaps this is equal to gamma 1, 2. It turns out the answer is, again, no. And now I go to the last one, and I observe that A plus B is equal to del U1 over del X2 plus del U2 over del X1. And it turns out that this is the correct expression for gamma 1, 2, which is equal to, of course, is that these were very special. Displacement only in one, displacement only in the two direction. In general, you can have a displacement in any direction. So this is the most general case. And in that case, this is the strain, and I can relate it explicit strain components as such. So it turns out that this is the expression for the shear strain gamma 1, 2 in terms of the displacement components. So similarly, for instance, right, there is a pattern. For instance, I can define gamma 1, 3. What you need to do is gamma 1, 3. So this was 1, 2, right? 1, 2, 2, 1, 1, 2. So I can go gamma 1, 3 is U1, comma 3, and then you switch the indices, U3, comma 1. Okay? And you can define gamma 2, 3 with a similar exercise, U2, comma 3 plus U3, comma 2. So now what we've accomplished is an explicit relation between the strain components and the displacement field components. Okay? And some sort of derivative is again involved, just like for the normal strain. Again, this is something that we had not done in 231, but we will make explicit and extensive use of it in this course. Okay, so please go ahead and write, and if you have questions, let me know. Notice that I am using a gamma, the old notation. I'm going to change that soon to have a more unified, a simpler expression for the strain. Okay, so let us now define the strain matrix, because we've built the individual normal and shear components. So now the mathematical definition of the shear strain, the strain, differs slightly from, especially, in fact, particularly for the shear strain components, differs slightly from our conventional choice. So let me make a note of it here. And the purpose is, it will look different, and you will ask, why does it look slightly different? Slight, but why not move on or carry on with the old choice? And the reason is that we want to have a, let's say, a simpler representation. A simpler matrix representation. And the definition is as follows. I will define the strain as 1/2 H plus H transpose. So remember, H was the displacement gradient. In terms of components, I'm going to write epsilon ij is equal to 1/2. So H has components H, ij, and the components of the transpose would be H, ji, right? You switch the indices. So that's equal to 1/2 Hij is u I comma j, displacement gradient, plus u j comma I. You can have a look at that expression, epsilon ij, right? Ij, ji. So if this is, let's say, 1, 2, 2, 1. If you switch the values of I and j, instead of 1, 2, you assign 2, 1, you still have, let's say, 1, 2, 2, 1, right? Suppose I had switched the indices. I put 2, 1. In this case, here I will have 1, 2, right? So in other words, when I switch the indices, the value of epsilon is not changing, which means epsilon is a symmetric matrix. Okay? So this is equal to epsilon ji. H is not symmetric. Whether you take the derivative of 1 with respect to 2 matters. So it's not equal to 2 with respect to 1. But because I have both ui comma j and uj comma I, epsilon is a symmetric matrix. Now let's go ahead and explicitly evaluate the components of epsilon 1, 1. I'll do this for only 2 components to indicate the relation between this expression, which I'm now proposing, and what I have derived individually for normal and shear strains. Well, so let's do 1, 1. So 1, 1, 1, 1, 1, 1, 1 over 2, u1 comma 1. Okay, so epsilon 1, 1 is u1 comma 1, which is consistent with what we have just derived for normal strain. So let's have a look at shear strain. Let's have a look at component 1, 2. Here I will put a but, because now there is a difference. Epsilon 1, 2 is 1/2 u1 comma 2 plus u2 comma 1. Compare with this one, right? So there's a factor of 1/2. So this is not equal to gamma 1, 2, but rather it is equal to 1/2 gamma 1, 2. So gamma 1, 2 is 2 epsilon 1, 2. So this is what we were using in ME 231 consistently. This epsilon 1, 2 is what we would like to use in this course. They only differ by a factor of 2. But the nice thing about using this expression 1, 2 instead of gamma 1, 2 is that every component of epsilon, right, every component, whether normal or shear, is based on the same mathematical expression. Okay, that is the advantage or simplicity of expression. So this is our choice. For shear strain. Okay, that's what we are going to use. Now let me close up this lecture with a explicit representation of the strain in terms of vector and matrix notation, just to remind you. So in matrix notation, I would write epsilon simply in terms of its components, 1, 1, 1, 2, 1, 3. Now I'm going to write 2, 1, but remember it's symmetric. So 2, 1 is really equal to 1, 2, 2, 2, 2, 3, and 3, 1, 3, 2, 3, 3. So we just need to always remember that it's a symmetric matrix. I wanted to remind you that because it is symmetric, although it seems to have 9 independent components, there are only 1, 2, 3, 4, 5, 6 independent components. And therefore, it was customary to express the strain in the void notation as a vector. So it's not a vector, but we express it as though it were a vector. And the notation was you start with the normal components, epsilon 1, 1, 2, 2, 3, 3. And I always recall by thinking, OK, I go back to the last two, so 3, 2. And then 3, 1, so 2, 3, 3, 1. And then 1, 2. Okay, 2, 3, 3, 1, 1, 2. Yes. And in void notation, you put a factor of 2. Okay. So in 231 notation, this would be gamma 2, 3, gamma 3, 1, and gamma 1, 2. Okay. This is just a reminder. We're not going to use the void notation, except perhaps for a few isolated instances. I will stick with the original expression epsilon ij, and I will not make use of the gammas. Okay, I will not make use of the gammas. All right, and one final thing. So now this is the strain expression. So I'm writing 1, 1, 2, 2. So this is the Cartesian system. If it were, let's say, the spherical system, this would be r, theta, theta, phi, phi, etc. Okay? Those would be the components. Now, there is one important concept that is associated with strain, and it is called the volumetric strain. The volumetric strain, at a point, defines the infinitesimal change in the volume around a point, scaled by the initial volume, right? So it's very related to the concept of strain. Changing the original, let's say, length divided by the original length. In this case, we're looking at the volume, and we call it epsilon v. Okay? So epsilon v is a quantity, it turns out, that is defined by the sum of the diagonal components of the strain. Okay? The diagonal components. And it turns out it's the sum of the diagonal components irrespective of the particular coordinate system you're using. So in other words, the volumetric strain is always equal to, so I will write epsilon ii, so it's equal to epsilon 1, 1, 2, 2, 3, 3 in the Cartesian coordinate system. It is equal to r, theta, theta, zz in the cylindrical coordinate system, and it is equal to r, theta, theta, and phi, phi in the spherical coordinate system. So it's always the sum of the diagonal components of the strain. The particular values, depending on the choice of the coordinate system, might differ. So the individual values are different, but irrespective of the choice of the coordinate system, this is always the definition of the volumetric strain. And physically, again, it means the change in the volume divided by the original volume. And it's, again, defined at a point, because strain components, in every case, they are defined at a point. Okay, we're right on time. Questions? Okay, so then I'll see you next time.